Hello, this is Jonathan Templin, and this is a lecture on an introduction to mixed models, in particular with an application to multivariate regression for EPSY 905, Fundamentals of Multivariate Modeling. In this lecture, we're going to talk about multivariate regression, but we're going to do so with mixed models. Prior to this, we've talked about multivariate regression in the context of path analysis. And path analysis I picked that to go first because I felt like the modeling itself within the framework of R and the Lavaan package was pretty straightforward. Certainly a level of difficulty above your typical univariate linear model, but nothing insurmountable without a little bit of patience. Multivariate regression with mixed models, however, is a different story. We are going to do this in R using the NLME package. And it's going to be a little bit more difficult to understand what's going on with the analysis itself. But buckle up. At the same time, it'll be something that we can get through. We have good reasons for trying to understand mixed models because they are a dominant paradigm, one of the two that are out there. And it's something that you might use later on in your scientific or graduate career. Particularly if you have analyses that involve multi-level models or some other type of repeated measures analyses. So you might see these quite a bit. But when working with path analysis, things were a little bit different than what we saw with mixed models. Now in theory, they don't have to be different at all. The same model, same estimation, almost the same estimation procedures and so forth. But what you're going to find is mixed models. With mixed models, you're going to have a lot bigger differences in how model fit looks. You're going to see that we have a very big difference with respect to how models are estimated, and that we're going to use a new type of estimation called residual maximum likelihood. And further, we're going to talk about how we can look at model comparisons using a Wald test. Remember, a Wald test before was parameter divided by standard error. It's typically what you see in the output or the summary statement for each model. But now we're going to construct Wald tests that involve more than one parameter themselves. And there's another rationale for why to do that. And finally, we're going to talk about how to compute R-square for each analysis as well. Again, our data example will be the same that we've used in the multivariate section of this course. In particular, we're going to take data from a 1994 study involving the role of self-efficacy and self-concept beliefs in mathematical problem solving. We're going to, again, go back to the multivariate regression version of this data example. This is something that we've seen in the prior parts of the class as well. The variables, once again, we have female here. We're going to talk about the variables that we use. We're using female here. We're also going to have, we're today going to use perceived usefulness. We're going to talk about mathematics performance as well. And the model that you're going to find here also includes, so here is our multivariate linear regression path diagram. We're going to have two outcomes that we're going to end up using today, performance and usefulness. And we're going to have three predictors of this, one being the sex variable, dummy coded with female being a 1, male being a 0. Another being college math experience. This is the number of credit hours of math experience a person took at the university they were at. And finally, the interaction between female and college math experience, or the product of those two variables. Now, in prior classes, we talked about what this path diagram represents, but let's just go over that one more time for completeness. Each of the boxes represents one of the variables in the analysis. And typically these boxes, when you see square boxes like this, particularly in the social sciences, that represents an observed variable. The arrows, the solid red arrows, represent what we call a direct effect. This is a regression slope. So this arrow connecting female, where the arrow terminates, is the dependent or endogenous variable. Any variable that does not have a direct effect terminating on it is called an exogenous variable. So these are the exogenous variables on the left, and these are the endogenous variables on the right. So when you look at this line right here, the direct effect represents, this first beta f comma perf, this is the regression weight of female predicting performance. And similarly, this is the regression weight of female predicting usefulness. So each of the regression weights are shown with those direct arrows. The blue dotted lines represent residual variances. These are the variances that are left over after prediction for the endogenous variables. And you'll see a double-headed arrow right here representing the residual covariance between performance and usefulness. Remember, the residual covariance describes how far off we are for both variables at once, helping to gain a little bit of information from each other variable in the analysis. Over on the left-hand side, though, you see a bunch of orange dotted lines. These represent the exogenous variances and covariances. Now, these are not explained. These are just allowed to vary. We understand that each of these variables varies, but we're not trying to understand why that happens to be. In your path analysis software, particularly in Lavaan, that package, we would find that each of these parameters were estimated. And that's the first big change that we see from path analysis in Lavaan to today with mixed models and NLME, in that in NLME, none of these are estimated, so they don't count as model parameters. So the big picture is that mixed models are used for a number of types of analyses. Right, so these are actually analogous to multivariate MANOVA, which you may have heard of before, or certainly you may hear your advisor speak about, and also talk about they're analogous to multivariate regression. So we see this quite frequently used when people say repeated measures, or a bunch of observations taken from the same person within a study. We can also use these types of models for multi-level models for clustered, longitudinal, and cross-effects data. So there's a lot of places. They're very general. And currently, kind of the state of the art for a lot of the software that we use sort of puts together mixed models with path analysis, in particular with the program M+, which is an expensive program. You can quickly get access to what we call multivariate structural equation modeling, which sort of puts the two together. But for us right now, and again, it still doesn't give all the options that we see here today, so it's one of the unfortunate things. The theory hasn't caught up with the software in this case, because there's really no difference between the theory in mixed models and the theory in path analysis. It's just that one comes from the mixed model group tends to come from more of a statistics camp, whereas the path analysis group tends to come more of from a social science, like psychology camp. So what you see is with different, like a lot of places in science, when there's the same discovery from different groups of people, you see different ways of looking at it and interpreting it. Unfortunately, the intersection between these two groups of people is very, very close. And so I'm teaching you this with mixed models now, because oftentimes you're going to have to face different audiences, some that might be more interested in mixed models and some that might be more interested in path models. So this is how it goes. The biggest difference, though, between mixed models and path analysis software is that assumed distribution of the exogenous variables. In mixed models, no distribution is assumed. They're not part of the likelihood. They're not part of the analysis. Whereas in path analysis, most software assumes these to be multivariate normal, particularly Lavaan. I will note if you use M+, it does not assume anything by default. So there's a combination that M+ starts to look a little bit more like mixed models. Now, the ramifications of not assuming what the exogenous variable distribution happens to be, mainly in a primary sense, affects the assumptions of which we might have with respect to missing data, particularly missing data for the exogenous variables or the independent variables. So by default, these mixed model software cannot have any missing data for the exogenous variables. So if those variables, if you have any cases that are missing, it will have a big problem. And you're going to see when we get into our analysis today that we will be removing the missing data itself. Now, removing that missing data is a topic for another lecture in this course. But what that means, the difference is, when we remove missing data, we're using an assumption that's called missing completely at random, which means effectively the missing data don't have any relationship to any of the results in the analysis itself. This is a weaker assumption than the assumption that we use for path analysis, which is missing at random. Now, I know they both look the same, but this assumption of missing at random is much stronger and much better protection for the analysis itself. what missing at random ends up doing is uses all available data, whereas missing completely at random, or at least for our analysis here, starts doing deletion of observations that are missing any variables. So deletion in general is not a good idea. So this is one of the drawbacks of the mixed model software. The other issue that we have is that mixed models do not directly allow endogenous variables to predict other endogenous variables, although you can find ways to trick the analysis to work. So the indirect effects are not possible from a single analysis. Right? So it's harder to do mediation in this analysis itself. Finally, mixed model software often needs, or mostly needs, variables to be stored in stacked or long format data where there is one row per dependent variable, as opposed to in path analysis, we call this wide data, where one row per person shows up. So what we're going to end up having to do is to transform our data to make that fit with the analysis. So I developed what I call a scorecard for the different types of analysis and models that are out there. This is sort of the feature that's available in each piece of software, and whether or not what's needed for it, and whether or not these things can be accomplished either by the old-fashioned stuff, the stuff you'd find in your typical multivariate class, multivariate ANOVA or multivariate regression, versus path analysis, in this case Lavaan, and mixed models, which in this case are NLME or LME4. And what you're going to see here is ideally we'd like every entry in one of these columns to be a yes, right here. But you'll see that nothing does it all just yet. So there's no, so here, we take a look at this. Can dependent variables predict other dependent variables simultaneously? This is sort of a path analysis feature. And we can in Lavaan. I should probably put here that yes, but put a star by it. It says, no, it's really difficult to do in mixed model software. But it is possible. But absolutely not with the original way of doing things. In a later lecture, we'll compare the original way to what we're doing now. The other part we'll talk about is, do we have variable-specific modeling options, right? So this is for precise model development, and the answer is no in the original way of doing things. What do I mean by that? That means that every predictor variable had to predict every outcome in your classical MANOVA or multivariate regression. But that is not a feature that we need to do now. So yes, we can do that with both. Lavaan directly means a little bit easier, and today we're going to see with dummy codes we can actually do that with mixed models as well. Next, we have the idea of robust maximum likelihood estimation, which helps for lepto or Platek-Kurtic data. Classical software does not. We both get that today. There is another version of maximum likelihood called residual maximum likelihood that we're going to see used today, because in maximum likelihood we get a biased estimate of variances and covariances. So residual maximum likelihood, or REML, is a very nice feature to have, particularly when you have small samples. In classical analyses, yes, we did get unbiased versions of this, and in today's example, yes, but that's one of the big holes in the path analysis software. There's a no there. Random effects, these are the parts of things that you're not going to get to in this class, but you would get to in a multi-level or a structural equation modeling class. They help different levels of dependency, so maybe you have observations nested in classrooms or observations nested across time and within a person. These are things that you might want to add to your model, and unfortunately the classical analyses do not allow those, but both of the analyses do the modern sense. We can have multiple covariant structures as well in the current sense, but we didn't have that before. We got better model fit indices in path analysis than we do for any of the other ones. And we have different denominator degrees of freedom methods, although we won't talk about those largely today, in mixed models, but not in path analysis. So here's the cool thing. Here's the problem with these last two columns. Really, we'd like to have a yes for both of them, to have one piece of software that does it all for us, but it's not available currently. So really, if we could add this to path analysis right here, it would be very effective. Or if we could add model fit indices to the mixed model software, that would also be very effective. So we are now going to do multivariate regression with mixed models. Before we dive in, let's talk about this model that we have built from originally. This is the same set of slides that you would see in the path analysis section when we added predictors to our path analysis. We have our two endogenous or dependent variables listed on the left-hand side of the equations. We have each exogenous variable listed on the right-hand side. And each regression has its own residual or error term. The residual terms have a residual variance. Here's for performance, here's for usefulness, and the off-diagonal has a residual covariance. We assume that these two residual variances follow a multivariate normal distribution. Now, before going much further, we're going to center our college credit hours at 10. This is to provide a little bit more information about how much mathematics each person has. And here's a picture of the distribution of college credit hours. You can see we picked 10 because it's roughly about where the median happens to be. And we also talked about endogenous versus exogenous variables. That still matters here, although oftentimes in mixed models we don't use that language to describe what a variable happens to be. But once again, endogenous variables are variables whose variability is explained by one or more variables in the model. Exogenous variables is the opposite, variables that have variability that is not explained by the analysis. Right. Now, I will note that these distinctions are not commonly used in mixed models. Oftentimes, the endogenous variables are called dependent variables or outcomes. The exogenous variables are called independent variables or predictors. Again, here is our path diagram that we're going to be pursuing today. The first step that we need to do, though, is to reshape our data into long format using the reshape function. So our original data had data that looked like this. Right up here, we had, for each, here's each person right here. Here's person 1, person 2, and so on. What we need to do is make it look like the following. We're going to take person 1 right here, and we're going to remember that we have two dependent variables for this person, performance and usefulness. And they have a 14 and a 44 for those scores, 14 and 44 here. So really we want both of these. We want one column for dependent variable right here. The reason we need one column for the dependent variable is because in the mixed model software there is only one spot to have a dependent variable listed. This is very similar to the LM function, the linear models function that we started the course with, where we have a dependent variable on the left-hand side of a tilde to indicate a model for it. So when we do that, we recognize that each person then, each person ID 1 here, is now going to occupy 2 rows of our data. Their usefulness, or the performance score of 14, right here, will be in the first row, and usefulness will be in the second row. And then we'll have some indicator of which dependent variable this happens to be. So this DV column you see here says performance or usefulness, describes which score shows up right next to it. Then for each of the other variables that we end up having, in this case we just have 2, female and CC10, you'll see that each of those gets replicated twice for each of those same scores. So it's like having 2 pieces of information per person. Now the way that we accomplish that in R is through the use of the reshape function. I created one of these functions in the EPSY 905R package, but I'm going to stick with reshape here because it's often what you find out there for help in R packages when you go forward. Here the reshape function takes our data set, our data frame from before. We have to tell it which variables we want to be in the dependent variable column, the name of the new dependent variable, the name of the variable that labels them, and the direction it needs to go. So this type of format is sometimes called long format because the data effectively gets very, very long and narrow. Whereas this format up here is often wide format. Sometimes we call wide format. So once we do that, the next step in the analysis is to remove all the variables from the likelihood function that have missing data. So this is where we go forward. This next set of syntax right here takes our brand new long data set, and for every score, CC10 or female variable that has missing data, or better yet, this is in which missing data is not true, it selects only the cases that have observations on all three of these. Any of those other observations, any of those that are missing, cannot be part of the analysis. So if I were to flip over to the R software to make this work, you can go ahead and take a look at my package here. Let's first take a look at the data before we go a little bit further. Data 01, this is the data that we used for Lavaan. This has been the data that we've been using for this section of the class for the past few lectures. So here you see each of the variables. If I use this reshape function right here, we end up with data 02 long. You see our reshaped data itself. But now, because you see in this reshaped data, data 02 long, there are 700 observations. You see that some of them have missing values. Right? This first one right here, person ID 3 did not have a score for performance. So what we're going to do is have to limit all of our observations here by taking this next step. So data 03 long cuts the number of observations down from 700 to 553, which is a big decrease. But when you look at that, now you'll see person 3, who only provided the usefulness score, does not have performance listed as well. So that also shows up in what we do. The next thing we have to do, and this is the big step for everything that we do in these mixed models, is we have to create a dummy code for dependent variable. Right? So why are we doing this? Well, the analysis itself, our mixed model analysis, only allows for one dependent variable from a data frame to be input into the model. So we're going to trick our dependent variable to really have two. And the way we do that is to create a dummy code variable that indicates which piece of data is contained on a given line or a given row of the data itself. And then with that dummy code, we're going to enter it into the model itself, because that can help us describe differences between the variables through a set of main effects and interactions. And yes, this is part of the reason why I've been drilling interactions throughout this course, because to use certain software, we have to understand interactions well enough to be able to build models to trick our way around them. So we have a single spot, we have one spot for a single outcome, and we're going to trick that. But let's just build the dummy code first. What we're going to do is we have to select what we call a reference variable, just like a reference group would be with the dummy code. Now what we're talking about is a reference variable, meaning we need to pick one variable where this dummy code happens to be equal to 0. So we're going to pick usefulness as our reference code. We could have chosen to use performance. We would have the same type of results, although the numbers would look different as we come out. But once we put them into a function like GLHT, which we can use again with this package, they would go back to the same results. The same results, same inferences would happen should we choose either variable as a reference variable. But for today, we're going to put usefulness as. So that means in my brand new data set, I am going to go over to this. In this data 03 long, remember this is our new data set that's long format that has no missing observations. I'm now going to create a variable called dperf, standing for dummy code for performance. We're going to initialize it at 0, meaning everybody gets 0 for this. And then for each case where the dependent variable is equal to perf, or performance, we're going to switch it to a 1. So now when I enter that, you'll see in the data themselves, everybody where this dv says perf gets a 1 here. And sure enough, dperf, this variable, is now going to be entered into our analysis, into our model, because it is going to be influential, or it's actually needed, to differentiate the scores from the two dv's in the analysis. So, as we did with the multivariate models with path analysis, we're going to start with building an empty model, because empty models should give us the mean and the variance-covariance matrix for our data back. However, I will say that the means that come out of this analysis, the variance-covariance matrix, will look different from the means and variance-covariance matrix that came out of Lavaan, and that's because that influence of the missing data. So when we scoop forward here, we're going to end up seeing what we end up having. Our empty model, again, for each one of the dependent variables just includes an intercept. So this is the intercept for performance. This is the intercept for usefulness. It also has an error term for each. Those error terms are multivariate, normal. And again, we have all the terms of the covariance variance matrix of error, or residual, estimated. The residual variance for performance, the residual variance for usefulness, and the residual covariance between the two. So first, we're going to build the empty model. But what I'm going to say is it's not so empty in this case. Because to build the empty model, again, I have to use software that has one spot for a dependent variable. But we're going to trick that software using our dummy code to giving us two values for the mean. So our empty model is sort of generic. Right? We have an observation's eyes outcome for the dependent variable. Now this is that column that you see here. This is their score. Right? So now we're going to model that with a predictor of the dummy code for which variable that happens to be. We'll still have our error term there as well. But what we'll end up seeing here is that when we have an outcome variable that has usefulness, this performance is equal to 0. Right? And so our model ends up giving us an intercept plus error. Whereas whenever this outcome variable or this predictor variable dperf is 1, it really says we're using the outcome performance, and what we'll end up getting is an intercept plus a main effect of performance. These two together will give us effectively what I'm calling beta 0 for performance. Right? Because adding those two together will work. What delta 1 represents then, actually let's go back and interpret this. Delta 0 then would be the mean of usefulness, and delta 1 would be the difference in means. Right? Just like we would see with a dummy coded variable for a different grouping variable. Only now this dummy code represents the different variables in our analysis. When I first saw this, my mind was blown, so this might be a little bit out there for you, but hang on, let's take a look at the numbers and see what we can find. And if it's still out there, just rewatch this lecture. I can tell you that if I were in your shoes, or better yet, my experience, I would have had to watch this lecture probably 5 times. This is a tough idea. Okay, so let's go into our analysis itself. We go back into R. We're going to be using the GLS function, which comes from the package NLME right here. Nonlinear mixed effects is what that stands for. The nonlinear mixed effects package is a great package. It's been written by one of my own personal heroes, co-written at least by him. Douglas Bates is one of the authors, and he's one of the authors of the LME4 package and the matrix package. So he's quite an excellent computational statistician for what happens. Now, this GLS package, what we end up doing with it, we have a score. We're telling it, just like with the LM package, this is just a single function. The model section of this function is where we have a score, and we put a tilde, and we tell it it's model. So it's 1 plus dperf. This is just like we'd see in LM. Right? Another thing that we'd see in LM is the data, so we have to tell it the data step. But there are a couple different parts to this that are different from what we get in LM, and that's because the different options that are present in this package. The first option, we tell it method equals REML, or REML. That tells us we want to estimate this using residual maximum likelihood. Again, residual maximum likelihood is good because it gives unbiased estimates of our variances and covariances for the analysis. That's important particularly when we have small sample sizes, because those variances and covariances go into the effects or the Wald tests that are given for each of the model parameters. So in short, having a biased version of those for the small samples can lead to type 1 error issues because the variances are biased downward, or we think we have less variability than we actually have. The next option we see here is correlation. What this is really trying to do is provide some type of correlation for the off diagonals of the variance covariance matrix. So what this is telling the GLS function to do is to estimate a symmetric correlation matrix. This type of option is all you need to put in. What it ends up telling us is there's basically estimating every correlation separately. And what we have to tell it is which variable in the analysis indicates the ID of each person in the analysis. So it knows which variables to covary. So this pipe in the middle of it right here tells us ID is the variable we need to worry about. The other thing that we need to do is to figure out the weights for the analysis. Also, these weights represent the variances themselves, and the way we're going to do this also is to say to estimate those similarly, but DV, or a different variance for the dependent variable that we see here. So now when we go and estimate this package, go back here, what we're going to see is the following. So we go and estimate this. It takes less than just a split second to run. In the analysis, we use the summary statement to get our information, and now we get a whole bunch of other stuff that comes out. Here, the very first bit of information is all we get for model fit. That's it. A log likelihood, the AIC, and the BIC. Now you'll recall log likelihood is important. We use that in likelihood ratio tests. Although now our likelihood ratio tests are going to be a little bit more curious, and I'm going to get to that in just a moment. AIC and BIC were also used for model comparison when we had non-nested models where we couldn't use the log likelihood or the likelihood ratio test. The next part that comes about is a correlation structure. Now, it's telling us the residual correlation, not the residual covariance. It's telling us that our residuals are correlated at 0.136, or that there is roughly a correlation of 0.136 between residuals once we predict them. Now, because this is an empty model, this is like the correlation we'd find in the population or the sample itself. The variance function goes and provides a weight for the variance of performance of 1. That's our dummy code. And it says the variance of usefulness is 5 times the variance of weight. We don't really typically interpret all this stuff up here. There's another function we can use to go and get the variance covariance matrix of the residuals. But now it tells us the part we're really interested in, that is the coefficients. This intercept value of 52.40986 represents the mean of, or let's just go back with what that means in a linear mixed model sense. That is the predicted value of the outcome when all the predictors are 0. I'm going to flip back to my slides because this value, this is the output that you'll see right here. Here is this. So what is our model again? It said y is equal to delta 0 plus delta 1 performance, or d performance plus error. Well, when this predictor is 0, that means this value right here, gamma 0, is the mean for usefulness. So that's our mean for usefulness. Now delta 1 then represents the difference in the mean for performance minus usefulness. Right, so it tells us the mean for performance is 38.46 lower than the mean for usefulness. And we can figure out what that happens to be using model comparisons as we go on. The other thing that we can do, actually let's do that. Going back to my R syntax here, what we can see is down a couple of lines below, we can actually use the GLHT function from the multcomp package to build that. So here, what we want to do, if we wanted to build the mean, this would be performance, and this would be the mean of usefulness. Right here, we would build the estimates. Right? We basically put a matrix in. Remember, this is the matrix that tells us which betas or which values of those coefficients we want to add together. We put the number in each of these categories is multiplied by the number in our beta vector, our fixed effects vector here, and summed together. So when we do that, we can build them together, we can submit them to GLHT, and the summary here will tell us the mean performance is 13.94. That was the sum of those two effects, 52.40986 plus negative 38.46901. The mean for usefulness then was just given by the intercept, which is this value right here. Now I want to note, when you have this dummy code for performance right here, and our output tells us it's negative 38, it's really not that big of a deal that we'd see a p-value equal to 0 here. And that's because it really does, we know that these variables are on different scales altogether. So because of that, we really don't have much to talk about with that p-value. It's just telling us which value goes where. Now, going back to the slides, the next thing that you'll see is we can actually get the variance and covariance matrix of our residual from this function getVarCov. So we submit our model object containing the model estimates into that. And it gives us this various covariance matrix. It also tells us the residual standard deviations for each variable. Right? So if we go down the list here, this first one represents the standard or the residual variance for performance, and this is the residual variance for usefulness. So this is sort of the crazy, crazy way of doing things. It's way, way out of the norm for what we do, and I have to tell you, I much prefer the path model version. However, I'm giving you this information because oftentimes you will want to use, if you have particularly small samples, the use of REML is the key to wanting to use this type of software for it. So REML right now isn't available in Lavaan. So this is why we go here. It's crazy, but we have to do it. We're going to next compare this analysis to the path analysis results we have, and I'll focus on my slides here to make this work. What we're going to have to do to compare, you'd think, well, we can just go back to the slides and the output from a previous lecture, and yeah, you'd think that would be the case. However, we have to make sure the observations align to make this work directly. So we have to go and figure out which observations we kicked out for this mixed model analysis, and then kick those out of the path model analysis data as well. So one way to do that is just take the data set we used for the GLS function, this data 03 long, and make it wide again. And that's what this reshape function is doing. It's telling it the specs that we need to do to turn this into wide data. And when we do that, we now get our data set, and we can take a look at what data 03 wide looks like, because it now is a wide format data itself. Furthermore, what we'll end up seeing here, if we wanted to compare this with our original data had 350 observations, whereas data 03 wide only has 311. That's because the observations where we had missing data were omitted. So if we were to go and mirror the analysis that we did in the mixed models with Lavaan, just to see what the differences happen to be, we would build our Lavaan mirror syntax. Again, this is the same syntax we started with in our previous lecture that talked about empty models, empty multivariate models. And we have our typical Lavaan output. So now our Lavaan output tells us this model is fitting very well for what we did. But what you'll notice is that our log likelihood in the mixed model, this is the value from the mixed model, or GLS, is not exactly the same as our log likelihood in Lavaan, and that's our first indication that things are a little bit different. Part of the reason why this is different is because we have REML, which has a different version, a different type of likelihood function as well. Moving forward, now we can compare our parameter estimates, and I'll just stay on my slides for this. These are the parameter estimates that came out of the GLS function over here, and this is from Lavaan. Right? And so now we can take a look at our variance covariance matrix. There is the estimate of our variance performance. we see in GLS it's 9.14 where it's 9.105 in Lavaan. Similarly, in GLS it's a little bit bigger for usefulness, and that's the impact of REML. REML has unbiased estimates here, whereas ML right here is biased. Slightly different though. We have a fairly large sample size, so it's not a big difference in what we end up seeing. The other thing we'll note is that we end up getting roughly the same means. The mean usefulness, remember that came from the sum, actually this would be mean performance, right here. This came from the sum of these two fixed effects. It's 13.941, and that's roughly the same here. So the REML doesn't affect the mean, the fixed effects, it affects the variance components. The mean of usefulness, though, was actually the same as well. So, and we also saw the standard errors were roughly the same too. Finally, the estimate of the covariance here is also a little bit different. Again, that's the difference between REML and ML. So let's talk about REML for just a moment. The use of REML, again, is the thing that motivates using a mixed model package rather than a structural equation modeling or path model package. And the reason for that is the ML estimator that we use in structural equation modeling or path analysis, in this case Lavaan, often gives us variance estimates that are biased in the downward direction, meaning they're too small. Now, if you remember when we did maximum likelihood and all that math that we put into it, the maximum likelihood of the estimate of the variance divides by n to provide that to you. And if you remember the analog to the standard deviation, the unbiased estimate of standard deviation had n minus 1. The same thing happens in these types of models. However, it's no longer n minus 1 for the variance, it's n minus the number of fixed effects in the analysis that shows up there for the denominator to make it unbiased. REML gives that to you. So the problem with biased estimates is that we may get incorrect p-values from them, particularly in small samples. So REML shows up. It is the difference between REML and ML is that REML maximizes the likelihood of residuals rather than the data. So that n minus the number of fixed effects is really what the residuals are represented. A residual is us taking our predicted value, taking the data minus its predicted value. So it sort of pulls the fixed effects out of the analysis. The cool thing is it gives us unbiased estimates of the variances and covariances. And so because of that, it is the default method that you find for estimation in LME, in GLS. If you're using SAS, or if you're using any of the other packages that have mixed models to them, you'll see that REML becomes the standard, or the default. But there's another catch to REML. Because we're effectively looking at residuals, that means the scale of the likelihood depends on the fixed effects in the analysis. So if we have two models with differing sets of fixed effects, we cannot use a likelihood ratio test to compare the two. So that complicates things even more. And again, I mention this because it'd sure be nice if we could put everything into one package to make this work. So what do we do to do model comparisons when we add a bunch of predictors to our model? Instead of using this likelihood ratio test that was nice and easy, the ANOVA function before, now we have to go construct something called a multivariate Wald test to get the same information. And this is a pain. This is very difficult to do. But I'll show you how to do it. The other thing I'll note is sometimes you'll see people, and myself included when I started learning about this, they'll use maximum likelihood with likelihood ratio tests to build an analysis, then switch to REML for the final version. But that also can lead to incorrect conclusions because the steps of the analysis using ML aren't necessarily the same as the steps that you'd take with REML. So really the idea is stay with REML. If you're going to use REML, use it the whole time and go through the pain of having to do multivariate Wald test if you really want to see whether predictors are needed when you add them to the analysis. So let's add predictors to the model and see how that works. Adding to predictors to the model is the same as we do in our regular regression models, the same that we do in our LM package. Remember in Lavaan when we added predictors, we had to start by building them with a 0 in front of them to see if we needed them in the model. We don't need this anymore, so that's nice. That's at least a positive for this approach. But a negative is we cannot use likelihood ratio tests to see if all of our predictors work. So what we're going to do is add in 3 predictors all at once here, female, CC10, and the interaction of the 2. I'm going to walk through what it means and how it works. Now when we add those predictors to the model, you'll have to realize that when we add a variable to predict things, the variable itself has to multiply. We have to not only add that variable, so for instance here we're going to add female as a predictor right up here, but when we do that, we also have to add the interaction of dperf and female. And that's because this dperformance separates the effect of female for both of the dependent variables in the analysis. Right? So let's walk through what this would be. Beta 0 would be the mean of usefulness. Right? Beta dperf would now be the difference in means, but you'll note dperf shows up in an interaction here, and here, and here. So a difference in means for males, CC equals 10, and actually the interaction that takes care of that. So again, how we have to interpret each of our effects, particularly in this dperformance variable, is like we would have seen with our analysis previous to this, with interactions, in that we have to go and say it's a conditional effect now. It's conditional on the 0 value of the interaction before for everything else, which is really frustrating. Similar for dperf by female. This dperf by female interaction, now you'll note there is a 3-way interaction here, down here. So we have to allow these other values to be 0 for this to happen. So what does dperf female mean? It's the difference in male-female when dperf equals 0 and CC equals 10. What does that mean? This is for usefulness. When dperf equals 0, this is the difference in means for males and females on the usefulness variable. So that complicates things, but it is the difference in males and females for usefulness when a person has, when a hypothetical person might have 10 college credit hours, right? So this zeroes out the CC10 variable, and this zeroes out the performance variable. So this main effect of female really talks about the difference in males and females for usefulness for people who have 10 college credit hours of math experience. That's how we interpret that. Whew. Yeah, take a deep breath. What about this interaction, this 2-way interaction of performance in female? Now, we have to consider it when the 3-way interaction CC10 is 0. So this is going to be what? Well, this is going to be the difference in male-female for performance. Right? It's actually the difference of the difference. It's the difference of male-female for use minus performance for CC10, right? And you're thinking, oh my goodness, what did I get myself into here? That's exactly what I think too. But again, it's something we need to kind of parse through. The next step, well, let's go look at numbers first, and then we'll get into the CC10 as another check on what we just learned. So, first thing we want to do is go add our variables to the analysis. Here is this model 2 mixed. What we'll note is an overall likelihood ratio test cannot be performed. It even says this, Rimmel comparisons are not meaningful. So, this is not good. But what we can end up doing is backtracking and trying to figure out whether or not we need these. Because this is sort of a first question, we'll get into what those interpretations of parameters are in just a moment. Let me go through and figure out whether or not which model. Let's tackle the issue of whether or not we want model 2 or model 1. Right? So going back to this, our null model is the model with a smaller number of parameters. In this case, we have 5 degrees of freedom, 5 parameters. So model 1 is the null model. That means model 2 is the alternative. So what we would want for a likelihood ratio test is to compare null versus alternative. But we're not going to be able to use that ANOVA function here because this REML comparisons are not meaningful. So what is the null hypothesis here? The null hypothesis is that all new betas in model 2 are equal to 0. The alternative is at least 1 new beta in model 2 is not equal to 0. Right? So this omnibus test that we're doing is testing for the difference in one of the new betas that happens to show up in model 2. So how do we do that? Well, the multivariate Wald test can be again achieved by using GLHT. And what we're going to do, because we want to really disentangle these effects, the first step I advise you to do is to build the analysis where you have in GLHT a specific matrix for each parameter of the model itself. Why I'm doing this is because some of these, in fact the new parameters that show up in model 2, we'll combine those to provide that omnibus test of a model fixed effects, of whether model 2 fits better than model 1. But then after that, we're going to go and take these to interpret the parameters themselves, to go and give us the model effects as we would have seen them in path analysis, or specifically directly for each variable in the analysis. So this is why I'm pushing the interpretation down a little bit, because we can take these, recombine them the way we need to be, and then get something interpretable out of them. So here, this is a series of values. Remember, in GLHT, we use this matrix function. The values in the matrix represent the numbers that multiply each of the betas that come out of the analysis. And if we go show the betas that come out of the analysis, if I go and grab this right here, you'll see that we have 1, 2, 3, 4, 5, 6, 7, 8 betas that come out of this analysis. So we'd want 8 numbers in the parentheses. Each one of those lines we're going to create is now a value for each specific parameter, meaning we just want one in one spot in the matrix function and zeros elsewhere. So the intercept occupies the first, dperf is the second. I'm just going down the list that I see them in output right here. Right? So dperf comes second, so that's a 1 here. Female comes third, it goes here. I'm naming them the same thing as well. So if I create values for each of these, then we can use GLHT to go and figure out whether or not model 2 is compared to model 1 using this multi-degree of freedom Wald test. The way we do that is we take the overall sig, or overall significance is what I'm testing. We put in it all the parameters that show up in model 2 that are not in model 1. And that's this set right here. There's 6 parameters. Female, main effective female, main effective CC10, interaction of performance by female, interaction of performance by CC10, interaction of female by CC10, and the 3-way interaction of performance female and CC10. Now remember, that's not all 8, because prior to this, model 1 actually had an intercept and had D-performance involved as well. So this is not the entire set of variables that we'd see. This is only the set of variables that differ from model 1. So there's 6 of them here, whereas they were in model 1 they had 2. So we combine those into a big overall significance matrix. This is what the matrix looked like, right? Just a 1 for each of these values. We use the GLHT function again, right here, to go get our effects. And now, when we put that into the summary function, we're going to add a new argument where we say test equals ftest, and in parentheses it gives this to us. And when we do that, it doesn't really give us an ftest. That's not cool, because it doesn't think degrees of freedom is available. But instead it does give us this global test right here, and that's what we're after. This is a 6-degree of freedom test, 1 for each of the parameters in the model. And this p-value right here tells us when this is small, right, this is the test of Model 1 versus Model 2, it's testing that simultaneously all of these effects are equal to 0 that you see right here. So this being a very small p-value says at least one of these effects is not equal to 0. And because of that, we would say Model 2 is preferred to Model 1. So that's a good situation to be in. So with that, let's get back to mirroring here. Okay, so now what we're going to end up doing is looking at our model themselves. The next thing we want to do is figure out the summary coefficient right here. Let's go and figure out what the values happen to mean. The way we can do that is by parsing them into those effects that we used to see in Lavaan, or in our path model analysis. Specifically, let's go and take the regression coefficients that work with usefulness and put them into regression coefficients that look like usefulness. Let's do the same thing for performance and fix those also for performance. So let's do that. All right, what is beta 0 for usefulness? That would be the mean of usefulness. And because the way we've coded our analysis, that means the intercept value is just that term. So this beta use 0 represents the I'm going to take the intercept that I created right here, this value for the parameter. So I'm going to recombine that into a new thing where I call it beta use 0. Similarly, the effect of female, the main effect of female in our analysis represents the effect of female for usefulness in the path analysis sense. Same thing with CC10, and same thing with the two-way interaction between female and CC10. So what you see when we create these brand new values for our betas is that if by all the variables where D performance equals 0 show up here, all the parameters where there's not interacting with D performance 0. And that's because that's what this means by the reference category. So we can build all of that and look directly at our effects. But these effects themselves are directly what we would have had directly in the output themselves. These are not. You can find a row of the output that represents each of these in our previous analysis. So if I scroll up to the summary statement here, you'll see that this intercept is the mean of usefulness. This is the difference between males and females in perceived usefulness. This is the effect of CC10 for usefulness. And this is the two-way interaction between female and CC10 for usefulness. Those are all directly coming out of the analysis. The problem is when we get to the performance variable, we don't have a direct effect of its mean. Now or its intercept. So previously we saw that the way we figured out its intercept is we took the sum of intercept plus D performance, which would give it to us, and that's exactly what happens. So to create our brand new variable, we create that using beta performance 0 by taking the intercept parameter and adding to it the main effect of performance. So this is the intercept, this is the main effect of performance, and that gives us the value of the or the intercept for performance itself, right? The value of performance when all the predictors are equal to 0. What does beta performance female represent? Well, this is the effect or the difference in males and females on performance, and how we calculate that again is we take female and we add to it the effect of performance on female. So this sum right here represents that. And that's what we end up doing right here. So here, this is our beta performance female. Of course, my syntax has an error in it. Didn't catch that before. Similarly, what is our effect of CC10 on performance? Well, it's the CC10 variable plus the interaction of CC10 plus performance. Actually, this should be female right here. And what is our interaction variable on performance? It's the original two-way interaction plus the interaction of performance as well. So we put all that together, we build a big matrix of betas, and we look at our effects with GLHT, and now we get the parameter estimates the way we wanted to see them had we seen them from Lavaan. These are direct parameter estimates themselves. So what does this tell us? Let's go through and try to interpret these. These are much, much more direct than what we would have seen in the model output. So again, the way we do this is we use GLHT, we grab each of the parameters, and then we combine them in ways using the interactions to go and separate the effects for each of the dependent variables. So the intercept, if we take our usefulness variable, these first 4 terms in the output are for usefulness. The intercept represents a person's perceived usefulness for a person who's male with 10 credit hours of college experience. That also knocks out the interaction. Female, this value right here represents the difference in males and females for somebody who has 10 credit hours of college credit. This is similar. This is the difference in males and females of usefulness. This is the slope for CC10 predicting usefulness for people who are for males. And so that knocks out the interaction. And this right here is either the thing that modifies the slope, right, the difference between males and female slopes, or it's the change in the difference in males and females per credit hour. That's how we look at that. So that's all for the usefulness variable. Now for performance, we do the same thing. The expected value of performance for someone who's male and has 10 credit hours of college credit is 13.689. The difference between males and females for 10 credit hours of college credit is 0.65. The slope of CC10 for males is 0.0987. And this interaction says this is the difference in slopes for males and females for CC10, or this is the difference in the means of males and females for performance per 1 unit of credit hours. So again, all of those terms are things that we saw prior to this with Lavaan. All of those are interpretations that we could have produced from Lavaan directly. The problem with the mixed model software is we have to go through all these steps just to get them, which is pretty frustrating. Finally, what we want to do is talk about our variance covariance matrix, and the way we do that is to go grab our residual covariance matrix from Model 1. This is pardon me. We want to talk about the R squared for each of these variables. So we actually have to calculate that ourselves. So V Model 01 is the residual covariance matrix for the empty model, and this is V Model 02 is the residual covariance matrix for the model with predictors. And so we're going to form R squared by taking a look at this difference right here of these diagonals, right? So this is the value of the residual variance of usefulness once we predict it with our variables, and this is what it was previously. So we take the difference between previous and current divided by the previous total. We can see that the R squared happens to be 0.06 for performance. Similarly, we do the same thing for usefulness and see that R squared is even more minuscule. So that is how we figure that out as well. So, are you with me? I'm there. I can completely understand if you're not. This has been a tough lecture to get through because of the nature of the mixed models. Again, I'm guessing if you're like me, you'll say, well, I like mixed models just fine, but I'm going to stick with ML and just deal with whatever the consequences are. Yes, they're a little bit painful to get through, but we can do it. I would advise you just listen to this lecture once again and try to work through it as much as possible. So the big difference here is that mixed models effectively are a lot more work when we have multivariate analyses. We effectively have to go and do GLHT. We don't get great model fit information. The chi-square itself doesn't quite work. We don't get standardized. We don't get any of these, pardon me, directly. We have to go and build each of these ourselves. But we do get REML. And for some people, that's enough. Depends on who you are. So with that, there's a lot to this analysis. There's a lot that go forward with this. But realize that this is an important kind of link between the two. And I hope at some point in the near future, there will be a way of combining all the features of both of these into one place in software so we don't have to go in through all these unnecessary steps just to get the thing to work well. All right, that's it for now. Thank you for paying attention to this point, and I will stop this here.